Greetings, AP Chemistry students. Today we're going to be talking about solids, and it's going to relate to intermolecular forces, molecular structure, all that good stuff. So, first of all, the properties of solids, and as you'll see soon enough, liquids, are determined by the types and strengths of their intermolecular attractions. And vapor pressure and boiling point are two properties that are directly correlated with the strength of these interactions. And melting point is also correlated, just not quite as strongly as vapor pressure and boiling point. So there's a pretty direct relationship between vapor pressure and boiling point. Melting point, it gets a little bit wonky because it doesn't take quite as much energy to melt a solid as it does to take a liquid and turn it into a gas. Um, Vapor pressure, if you're unsure, is if you have a container with a liquid in it, it's the partial pressure of the vapor above that liquid, is what vapor pressure is. Right? So there are several different types of solids. There are amorphous solids, which have a disorderly structure. Glass is an example of this. For those of you who are geology nuts, obsidian, which is volcanic glass, is an example of this. And then there are what are called crystalline solids, which have a crystal lattice structure associated with them. And there are three different types of crystalline solids, as we will see. There are ionic solids, which we covered in Unit 2. There's covalent network solids. There's molecular solids. I'm sorry, there's a typo on this. There's four types of crystalline solids. Metallic solids. So I'm not sure why that says three instead of four. Now, for ionic solids, which you should know this already, they are formed by the attractions between positive and negative ions, and they form a crystal lattice structure. And ionic bonds are usually weaker than covalent bonds, and the strength depends on the magnitude of the charges. But they form this lattice structure where you have the positive and the negative, and then you have negatives and the positives, and they kind of form this three-dimensional lattice structure. We've talked about this before. And Coulomb's law comes into play with understanding the strength of ionic bonds. And properties of ionic compounds are, of course, that they conduct electricity when they are melted or dissolved in water because these positive and negative charges can move around. And they are brittle because of their charge repulsions, where if you line up two positive charges with each other, it repels. This right here kind of shows us sodium and chloride. That's an ionic solid right there. We'll come back and look at this again. The next type of solid we're going to look at is what's called covalent network solids. In covalent network solids, atoms are bonded into a two-dimensional or three-dimensional network. And these can be formed from nonmetals or from covalent compounds such as silicon dioxide or silicon carbide. Silicon dioxide, when it forms this covalent network solid, it's called quartz, which is the main ingredient in sand. Right. And these three-dimensional network solids are very rigid and hard. Diamonds being the hardest substances on Earth. Quartz, if you're familiar with that, is very, very hard substance. Graphite, on the other hand, is soft because the layers can slide past each other. So diamond forms this tetrahedral arrangement around the carbons where each carbon is bonded to four different carbon atoms. So this carbon, it's sp3 hybridized, and these bonds in three dimensions are incredibly strong. The carbon in graphite, it's sp2 hybridized. It forms a trigonal planar structure, and it's very strong in that one dimension. But then between the layers, those layers are just held together by dispersion forces. And so that creates some significant weaknesses in graphite where it can actually, the layers slide past each other. And pencil lead is made of graphite. And as you're writing with it, those layers just slide off and then they form dispersion interactions with your paper, which holds the graphite in place. But it's not a very strong attraction because you can then use the other end of your pencil, the eraser, and you can just rub that graphite right back off of your paper. Right? So that's some covalent network solids, which is our second type. This kind of shows how the carbons in graphite are kind of arranged. This shows quartz, which is a network solid right here with this hexagonal arrangement. Uh, and then this is quartz glass, where glass is made by cooling this very quickly, so it doesn't have time to form the crystalline structure that's very rigid. It's amorphous. It has uh, an irregular shape associated with it, which also tends to make it quite transparent. Molecular solids are just solids made of molecules. They have very strong covalent bonds within the molecules, but very weak intermolecular forces, relatively speaking, between the molecules. And as the size of a molecule increases, the magnitude of London dispersion forces becomes significant even in nonpolar substances, which is what allows things like, for instance, candle wax to remain a solid at room temperature because it's being held together through dispersion forces, even though it's nonpolar. Um, Whereas something that is polar and would have dipole forces such as acetone or nail polish remover. That's a liquid that very easily turns into a gas at room temperature. Uh, but acetone is a much smaller molecule than candle wax. So candle wax, or paraffin as it's also known, it remains distinctively solid at room temperature, even though it's only held together by London dispersion forces. Molecular solids generally have low melting points, and they are non-conductors of electricity because the electrons within a molecule are very tightly held. So, typically non-conductors of electricity. And molecular solids can also be very large molecules or polymers. DNA is an example of a molecular solid. Ultimately, polymers are when you take regular repeating compounds and you make a structure out of them. For instance, polyvinyl chloride is a polymer, and that's essentially made, if I can bring this up, by taking, let's hold on. How do I make a new one of these? New. So we can take vinyl chloride, which looks a bit like this. And you just take this and you repeat this pattern over and over and over again to polymerize it and make a giant chain of this. This is called a vinyl chloride, and you just make a big chain of that. And that's what's polyvinyl chloride, or PVC, which is used to make plastic pipes and things like that. And then the fourth type of solids is metallic solids, which, once again, you should know this already. These have the sea of electrons, the delocalized mobile electrons, and non directional bonding. Metals have high conductivity, malleability, and ductility because of those mobile electrons. And once again, this is from Unit 2. Okay. So we're just going to look at a couple more things here. This shows, let me go back to this previous slide up here. This slide right here, you can see the diamond. That's a covalent network solid. Sodium chloride is an ionic solid. And then this is ice, where the water molecules form this very regular hexagonal pattern associated with it, where they form hydrogen bonds between the water molecules and they form this crystal lattice type structure. The fact that it forms this hexagonal structure with essentially a hole in the middle of it, it causes ice as it forms to expand, which is why if you were to fill up a container with water and you put it in the freezer, that container can crack as the water expands as it forms ice. This six-sided structure also explains why snowflakes, when they form, tend to be six-sided objects as well. So let's take a look. This kind of summarize a little bit some of the properties. You can go through and peruse this PowerPoint on your own a little bit. And this shows melting points and heats of fusion for several solids. You'll notice that the ionic solids down at the bottom of this list have very high melting points and heats of fusion. The non-polar covalent ones have very low melting points and very low heats of fusion. Heat of fusion is how much energy is required to actually melt it.